Welcome back. In this lecture, we will introduce unsupervised learning and clustering. Now, here's our objective. One thing I'll say up front about unsupervised learning is you are essentially handed a pile of data and need to make some kind of conclusion on it. Now, all of us have been doing this since we were kids and learned how to compute an average. If you think about it, an average doesn't have any specific meaning about that data. It's not tied to a particular prediction or an outcome. And we all know of cases where computing the average value of something is really useful and important to know because maybe it's associated with what we expect will happen in the future. But we also know a lot of cases where computing the average is not going to be very useful in predicting the future. But it's a very useful tool on the whole. Unsupervised learning is much like that. And in fact, it's really easy to argue that average itself is an unsupervised method. And that's going to be the focus of this particular lecture. This contrasts directly with supervised learning, where we have some kind of target. We have some data where we have some information about it, whether it's raw data like pictures or something like that, or we have measurements of the data, and we want to determine something. We have a target value, or a target label. Unsupervised learning, like I mentioned before, kind of like average. You're just trying to make some determination about this bunch of data that you have. Maybe you want to group it in a certain way. Maybe you want to identify an anomaly or a trend. That's what unsupervised models are designed to do. And they're very useful when you have no class data. It's also useful in the case where maybe the times where you have class data is extremely infrequent. Or when you do have class data, it's because there's maybe a shift in data distribution, and identifying anomalies is a more sensible way to do business. And that's kind of the main intuitions behind why this approach to machine learning is important. So clustering is one of the key use cases for unsupervised learning. And here what we're seeing in this diagram is we have a feature space in 2 dimensions that is plotted. We have feature x1 and x2, and the little dots are just samples in our data set. Now, we colored in these points in different colors, but we're just going to say that these colors, they don't represent a class, they just represent a cluster. So maybe we ran a clustering algorithm on the data, and it said, hey, these purple things go together, these cyan things go together, and these yellow things go together, and that's it. It's not based on any knowledge or history or supervised model. And so the whole idea with once you have clustered them this way is, each point in a given cluster, it's colored that way because it's closer to other points within its cluster. So this cyan point we have circled here on the slide, we want it to be closer to the middle of that cyan-colored cluster, and we want it to be far away from the center of the purple cluster. And that's kind of the intuition behind clustering. There's a couple main ways of thinking about clustering. First is partition clustering, where you want to group samples into disjoint sets, hence the word partition. There's also hierarchical clustering, where you can have levels of clusters. So a cluster can function as a container for more clusters. You can think of it as like a set of kitchenware where multiple containers can fit inside a larger one. Clustering algorithms will typically use a distance function, and the ones we'll cover in this course will. Shown on the slide is our good friend, the Euclidean distance function. And often it will make sense to want to scale our features because since we're dependent on the distance function, we want to avoid cases where a certain type of feature has an outsized impact on the result just because it's scaled differently. And there's many different ways to do this. A lot of it depends on the distribution of the data within that feature. And you could even scale different features differently within the same problem. And so just to give you some intuitions, when you clip features, this is normally in the case where you have some extreme outlier values for that feature, but otherwise they fall tightly within a range. Logarithmic scaling makes a lot of sense when you have power law distributed data, things such as number of social connections in social media. If you look at events like number of casualties in a terrorist event, that will also follow a power law distribution. Z-score is more designed for things that follow a normal distribution because that's relying directly on the mean and standard deviation. So that concludes our introduction to unsupervised learning. Stay tuned for more content.